first I will talk about the sensors types. So my topic discussion, first the sensor, why we need the sensor, then the sensor taxonomy, then MOS sensor, I will go for the MOS sensor, then what is the mechanism of the MOS sensor, then advantage, what we have in the MOS sensor, what are the challenges are faced in this MOS sensor. So at the beginning, first first thing is why this, what is the sensor? That fundamentally a sensor are the devices that detect some feature quantity of measurement object. So that quantity may be anything, that maybe it's behavior, or maybe it's distance, it may be weight, it may be it's many other properties. Then that whatever it is measuring, that should be converted, that quantity should be converted to a readable signal. Now that readable signal may be displayed or may be sent to some other device for next processing. So that is the mainly the sensor. Now why we need a sensor? Because before preparing a sensor or discussing about the sensor, first we need to understand why we need a sensor. So what are the purposes where which we are going to prepare a sensor? So in presently we have many types of sensor. In the picture itself, you can see so many sensors are already present. So these sensors, but they are for different purposes. They are used for different purposes. So the why we need sensor, mainly whenever we think that we want some automation or we want to monitor so some activity, then we have to we require some sensor. Then for the automation, if I talk about, that maybe factory or in the industry where people's people's want to decrease the human involvement. So maybe the jobs where it is dangerous for the human, so there this automation is very much required. And if it is a stressful or laborious work, there also some automations are required. Or if it is a tedious work or same work it is continuously you have to do repeatedly, then that type of applications also we do automation. So whenever we do automation, so for the for automation we always require some sensor. Now for the monitoring means it may be any activity, it may be health monitoring, it may be other activity monitoring for maybe industry purpose or maybe health purpose. So that type of monitoring also we require some sensor. And presently always we heard the word that IoT. So for the IoT application also we require the different type of sensor, because there we talk about that we have to communicate, all the devices should be communicating to each other. So whenever we have a communication from one end to the another end with the help of either with the help of human or without help of the human, then there are always requirement of different type of sensors. So in overall, if I want to tell, for any safety, security or surveillance case or monitoring or general awareness or maybe weather monitoring, there also we require different type of sensors. Now so these are the applications where we may be requiring different type of sensors. Now maybe in maybe the space also, in the space also number of sensors are required for monitoring and for even proper working of the devices. Now in the human, first sensor, if we talk about the example of the sensor that we have, human sensing and organs. Now, so these are the most important we in daily life we use vision. So eyes, these are optical sensor which sees the light. Hearing, we have ears, that is the acoustic sensor, so that is using the sound. And touch, that is the skin. For the touch, we have the we can, if any heat is there or anything, we can easily can be sensed by that skin. Similarly, nose and tongues are there, which are actually the vapor phase chemistry are involved, or the liquid phase chemistry is involved for the sensing of this this type of sensor. Now what we have a counterpart of this. So So whether we can make the similar sensor or not. So to understand that, we have to understand how many types of sensor, because all types of property to sense all the different properties, we require different type of mechanism. So the main our objective will be to interact with the environment in a flexible manner or intelligent manner. So after that, whatever signal we will be getting, that will be extracted and that will be given to the next application for the further processing. So a system, if it is having if it can see or it can feel the environment, then that can be easily trained. Like we know that the robots and different other machines, those can be easily trained whenever it can see and it can sense itself. So maybe there are a number of processing is required, but before that, first step is the sensor. We require the sensor first, and that if we can make it intelligent, then obviously that will be beneficial for us, and then we have to make the necessary processing of this real-time information. Now, the sensor taxonomy, if we divided that in place, if we think about that a device is a stationary or it is moving device which is trying to sense the outer environment and it is trying to move with respect to that information, then based on that we can divide whether it is the internal sensor or maybe the external state sensor. Internal states means those sensors actually they will be used to measure the positions or velocity or acceleration of that machine or it's any of the portion, maybe joint or any other actuators. So these devices are actually, those sensors are normally we usually use. Those are actually the different type of tachometer, potentiometer, optical encoder, accelerometer. So those are so mainly here we use the position sensor or velocity sensor or torque sensor. And external means from the outside environment. So with that relation, that machine will change its kinematic or then its torque, means surrounding whatever they have, with that they will map it, and with that of the information from the sensors it will use and change its motion. So those sensors are tactile sensor, proximity sensor, vision sensor. So these sensors are very much required for or maybe the force or torque sensor. So based on this, we can divide into two types, or otherwise if we divide based on whether it is active type, active or non-active, means whether it is emitting any energy or not. So based on that, say if it is emitting energy, and based on that it is, means in the mechanism there is that energy has to be emitted, and after that it is receiving that energy which is reflected from some of the surface, then we are calling it active type. So radar, sonar, those are the active type. Or passive means we can take an example of camera, means it will do only the observation, it will receive the energy and do the observation. So that is the active or non-active versus non-active. Now similarly, whether it is a contact, if we require a contact for the sensing, then it is a contact type, or otherwise non-contact. Similarly, visual, non-visual also. The visual, under the visual, actually image processing, video camera, and the CMOS camera. So those CMOS image sensing sensors, those will come under this. Now that contact or tactile sensors. So these sensors actually will use some transducer. Now this transducer, these are actually here these sensors are examples are the potentiometer, strain. So what they will do, they will detect a change in the position or velocity or force. So some examples, if I say, or maybe the type, one is bumper or tactile type. So bumper means actually it will detect whether it will touch or not. It means like a digital yes or no, but it cannot give the information how the contact, whether it is how much hard it is touching, or what that touching. So those information cannot be achieved. So but some other tactile sensors are there, they are more complex, where we can use the information which is received from the sensor, whether in which direction it is going or how much it is touched, whether relative what is the rate of the relative movements, that can be we can receive from the tactile sensors. Now, if I give some example of contact or tactile sensors, you can see in the figure we have some piezoelectric sensor where we have two electrodes. If we give a pressure on that, so those there will be a change in the voltage, and that can be sensed as a change in the pressure and other things. So similarly, switch also, normal switch also, which can be on and will do only on and off, that also can be used as a contact sensor or tactile sensor. Now, these type of sensors in the simple switch, we can see in the circuitry how it works. If we give a force here, whenever it is having a force, then it will touch, the pins will touch the totals in the below the points, then the total circuit will be complete and there will be electric flow and we will have the voltage measurement. So based on this phenomena, we can have this type of working of this type of sensors. Now, multiple number of sensors can be used in an array or column. We can use an array, means row and column, we can place them and then we can use we can arrange them for a large sensing. Now, the tactile sensor, that what it is, the major component is we have four components. A touch surface should be there, then transduction medium, which will convert the force to a electrical signal, then the structure and the control and interface. Now, this transduction method, it can be of different type. It may be resistive, it may be piezoelectric, or it may be capacitive, it may be mechanical, or maybe optical transduction also. If it is a resistive transduction, then what we will have? We'll have in the figure you can see in this method, we have a rubber type conductive material between two electrodes. And in normal case where there is no force, then the distance between those two electrodes are higher, and in the between we have conductive rubber. Actually, due to this, the resistance will be high. But whenever we have an object which is giving a force, so that the conductive rubber will spread and the two electrodes will come near to each other. In that case, the resistance will decrease. So using that, so the conductivity will be changed, and we can, in that way we can sense it. Now, so similarly, it can be of capacitive type, it can be of mechanical type, then it can be of you can see if it is a capacitive type, then also if two terms between we have elastic dielectric. So elastic dielectric layer. So if the force is there, then those electric dielectric layer that will be spreaded and two electrodes will come near to each other. As the distance is decreasing, obviously our induced currents also will mainly the capacitance will increase. So due to that, we can have the change in the signals. Obviously, that can be considered as a sensing. So now I will not go deep on each and every one. Then optical transduction, I will just go to that. We can see the optical transduction method. Here we have a rubber sheet, and below that we have actually optical waveguide, where the lights are passing. In normal wave, those lights are passing, but whenever we have a rubber sheet, on top of that we have an object which is giving a force, the pin of those rubber sheet that will be pressed on that waveguide. So due to that, the internal reflection will change and more lights will be reflected, and due to that, there you can see the below the view in the view A, there we have from this point, so we have different light spots. So from this we can understand in which position the force is applied and where is the more intensity. So like that, this type of optical tactile elements can be used to sense the the pressure. So this way we can these are the tactile sensor. Now, so these type of tactile sensor actually are mostly used in the robotic applications, in the robotic hands. So there in the figure you can see 3-axis tactile sensor which are mounted on robotic fingertip. So earlier whatever I have shown, that is only one. Now this one that can be it can be placed in a hemispheric tactile sensor. You can see in the left side. Here you can see we have 3 different points where hemispheric tactile sensors are placed, and this is the total movement sensor, and this sensor is repeated, is in a row and column way. It is placed in top of a robotic finger. Now each element it can sense, and from there we can, as they are used in a row column, so that can be that can sense easily the total movement of total how the material is, which is being touched, how the material is, what is the movement of that. So in that way, this type of tactile sensor can be used. And how, whether we are see in this here also we have this robotic hand. So this type of hand easily can sense whether this how much pressure it is applying on the material, or how much whether it is hard or soft. That also can be sensed from this type of sensors. Different tactile sensors which are actually placed in a skin. So prosthetic skin and robotic application that can be used this type of skin sensors. So these are stretchable tactile sensor. So easily it can be placed on top of, say, like similar to a skin, it can be placed on top of the sensing elements, means the position where we want to sense. So whether it is a robot or any other system, we can easily place them and we can sense it from there. So these are about the tactile sensor. Or it can be used for prosthetic fingertip. So there also we can use, and even we can use the resistive sensor also in those cases. And the resistive sensor then can be placed on tip of the finger, and then that can be can easily detect the material, whether we are touching any maybe we are touching any hard material, or how much is the weight, or what is the density of the material. Those things can be measured from this type of sensor. Now, non-contacting sensor, there we have many things, means visual, optical, then capacitive sensor, resistive sensor, ultrasonic sensor, sonar, air pressure sensor. Now from here, we today's whatever we are going to discuss, that MOS sensor. This MOS sensor actually will come under this non-contacting sensor. Means directly we are not contacting. This is obviously the gas. We have to measure the gas whether it is present or not. We have, so we cannot see in bare eyes. So those type of applications we have to use. Other than that, now proximity sensor we have to do some if we want to measure whether any object is nearby or not, whether this material, any intrusion is there or not. Those type of applications we have object detection for the object detection, or collision avoidance. We have proximity sensors. So commonly available actually sensors are photoelectronic or optical sensor, inductive proximity sensor, maybe it may be capacitive also, it may be ultrasonic proximity sensors also. Now now a little bit about the resistive sensor. So normally resistive sensor, whatever we have in the market, so that sensors actually if we bend those resistant bands, those sensors, then its resistance increases. So from there also, if there is any bending, there we can measure. If we we do the proper calibration, then we can measure how much it is bent and all. So if like a potentiometer is there, which can be also used as a position sensor, means if any sliding door is there, that also how much it is slided, that can be measured from this potentiometer. And similarly, photocell, that also in different applications we use the photocell for detecting the whether there is illumination or not. So then we have IR sensor. Now in the IR sensor we have reflective, this is actually reflective sensor. Now here we have a emitter and a detector photodiode. Infrared will be emitted, then a beam of light will be reflected on the surface, and then it has to be detected by the detector. So detector, we have a photodiode, and this type of application actually we use for object detection or line following or wall tracking, for those applications. Now what is the drawback? We have the drawback that if there is ambient light is present, then we will not be, this type of sensor will not work properly, and that will be susceptible to the reflection from the other objects. So we have to have we have to use some other sensors which are advanced one, like we have here we have another sensor, IR sensor. Now this distance sensor, what we have, again here we have a IR emitter, then focusing lens, and then a position sensitive detector. Now the sensor that show from the shaft is shown in the figure, that which is sensing from 10 centimeter to 80 centimeter. So it can sense a location of the spot, and because here we are using a focusing lens, obviously it is having better sensitivity from the previous one. Like we can have the laser range sensor, we can which range will be more. We can see if you, instead of using the infrared, if we use a laser, obviously our sensing range will increase. So 2 meter to 500 meter, then resolution also will increase. So this type of sensor already you may have heard, and these are used in different applications. Then we have ultrasonic sensor, which emits a quick burst of ultrasound, which we cannot hear. And those sensors actually, they will wait to receive the echo from the object, and that will be, and then once it receives, then it will measure the elapsed time. Now from there, how much distance it has covered, and what is the, that will be calculated from the time taken to receive the signal. So from so like that, so here we require a transmitter and we require a receiver also. Maybe sometime both one and transmitter and the same circuit can be used for transmitting and receiving purposes also. Now about the vision sensor, in last yesterday there also discussion about the vision sensor of image process, CMOS image sensor. So that is the most important sensor. Present day people are researchers are working on to improve the vision of sensor. If any system is having a vision, and if there is intelligence can be included on that, then that will be beneficial for any type of monitoring or any type of detection. Now, so there are many sensors I have given the told about the names, and some of them I have discussed about the what the physics based on. Now among them you have seen that we have image sensor, we have a proximity sensor, we have different type of sensor, whether it is a tactile or it may be other contacting or non-contacting. But now I will come to the sensor which today I will want to concentrate mostly, that is the MOS sensor. So actually this MOS sensor, the MOS full form is metal oxide semiconductor. But here metal oxide means, this is the one word, means we are using a oxide of a metal and then semiconductor for the sensing purpose. Actually it has been normally we know that any semiconductor electrical property, they are sensitive to many properties. Like electrical resistance of a semiconductor is very sensitive to the presence of impurities, because if we change the impurity, obviously the resistance will change, and that is also even in the volume. It may be in the volume or it may be in the surface. So using this phenomena, it was demonstrated that in 1953 the effect was first observed in the germanium. Now later it has been seen that zinc oxide, the thin film, which is heated up to 300 degrees centigrade, and then it senses the presence of some trace of reactive gases in the air. Now, so you think in 1953, first it was demonstrated for the germanium. Now, after that, zinc oxide, first it was seen that whenever it is heated to 300 degrees centigrade, then it had become sensitive to the presence of traces of reactive gases in the air. Sensitive means its electrical properties are changing. Now, similar property was were reported for the tin oxide also. So, with the higher stability. So, same whatever we have was seen by the researchers for the zinc oxide, same was seen for the tin oxide also. But the results was better. It was having more stability. And once this type of phenomena is observed, then people have started to commercialize this type of to use this material, means this tin oxide or zinc oxide materials, to use them in the gas sensor for sensing of the gases. And then they have started to commercializing those gas sensors. Now, what type of different other type of gas sensors also present there? Like we can talk about the crystallite type gas sensor or electrochemical type gas sensor. I think the previous lecture, the today's morning first lecture was the electrochemical type sensors, not the gas sensor, maybe it was the sensor. So same phenomena, using a similar phenomena, we can have the gas sensor also. But catalytic type gas sensor also, there we can use a detector element which contains a catalytic material, and it is sensitive to those combustible gases. So when those combustible gases will burn, then those whenever in presence of the detector only, they will increase the temperature. They will increase that combustion will increase the temperature, and from this temperature it will be sensed, and there will be a rise in the resistance. So like that, and like using this phenomena, we can detect whether there is a combustible gases they are present or not. But other than that, we have MOS type sensor, which are presently very much in the interest of the researchers. Now, here I have shown one figure of some MOS sensor. This is a MQ5 MOS sensor. So there are a number of MOS sensors are in market also. It is available, which are based on normal MOS type, or maybe electrochemical type, or the catalytic type. For different gas measurements. So MQ2 for the LPG or smoke, MQ3 for alcohol and ethanol smoke, MQ4 for methane, CNG gas. So there are a number of gas sensors are already present in the market. It's available commercially. But let us first understand why we'll go to MOS sensor and why we are talking about this type of structure for the MOS. Why not other? Before that, let us first try to understand what is the mechanism here. Actually, this is based on the solid state device. Okay, the characteristic of this type of solid state devices was researched or was studied by numerous researchers, and it is seen that this type of sensor is reversible in nature. So means in the presence of gas, their characteristic will change, and if we remove those gases, that characteristic will remain as it will be reversed to the earlier stage. So it is a reversible type. So then we this is, if it is a reversible, then that can be reused for a long time. So in addition to that, the conductivity change of gas sensing material, the detection of this reaction can be performed by measuring the changes of capacitance, work function, mass, optical characteristic, or reaction energy related to the gas or solid interaction. Now you will see here, it is not only one property. We can measure the conductivity also. We can measure the capacitance also. We can measure the work function also. Means this gas material, that it changes the conductivity, and that conductivity is for the due to different it affects the different properties actually simultaneously. So it may be measured through the capacitance change, or maybe the work function change, maybe the mass change, maybe the optical characteristic change. So there is not only one way to measure the properties. So we can, how much sensitive that sensor is, or how much it is the sensing that can be done from different properties. So actually the MOS property, that semiconductor property, normally changed. The structure may be changed, the doping concentration may be changed, so or capacitance may be changed, or work function of the metal that may be changed. So different thing may be possible when in presence of a gas. So till now, the beginning, the most successful or investigation was performed on the tin oxide, zinc oxide, and TiO2. So type of materials are actually used for the MOS gas sensor preparation. Now, the sensor characteristic, actually already I have told, it can vary the crystal structure, the dopant, and preparation. Those sensor characteristics that can be controlled through the preparation technology also. Means how this device or this sensor film is prepared, that can be that will actually dominate whether it will sense or at what degree of temperature it will sense, or what material or what gas it will sense. So operation temperature is also another important parameter. Now, so there are so many variables are there, and there are so many ways to control or to characterize these sensors. So interest of the researchers or engineers was given to prepare the gas sensors using those material for sustainable development of the our future technology. Now, at the beginning, there was a problem of the fabrications, but now day by day, the fabrication technology also improving. So new structures can be prepared, and we can go for smaller devices. So various materials synthesized in form of porous ceramic and deposited in form of the thick or thin film are used as active layers in such gas sensing devices. Now here, the thick or thin films, so this is a concept, this actually relate to the fabrication process. Now how much thin film we can fabricate, that depends on the fabrication technology, how much it is improved. So nowadays we can take help of MEMS technology, means using normal fabrication technology also we can fabricate this type of MOS gas sensors. So there are so what is how it works? Actually, it is based on a chemical process where is detected gas by means of selecting chemical reaction with a reagent, mainly utilizing the MOS chemical detection principle. So whatever material we use, mostly all are following a similar principle. So we call it chemiregister. Okay, the principle of the chemiregister. So these are actually typically those MOS gas sensors are fabricated by single or mixture of metal oxides. So what are the metal oxides normally used? So tin oxide, titanium oxide, indium oxide, tungsten oxide, or nickel oxide, or zinc oxide. So there are many, or maybe combination of them. Okay, we can use the combination of them, and then so using the combinations we actually can select which gas should be sensed. Now it has 4 parts. So MOS gas sensor actually will have 4 parts. One is the sensing layer, then the insulating substrate, then the 2 contact electrodes, and 1 heating element. So the heating element, actually this heater is separated from the sensing layer, and the sensing, there will be a sensing layer, and in between there will be a insulating layer. So it is separated, the heater is separated by a insulating layer. Now, what is the physics behind this? The change of electrical properties of metal oxide semiconductor due to the absorption of gas molecules is primarily connected with the chemisorption of oxygen. The molecular oxygen absorbs on the surface by trapping an electron from the conduction band of the semiconductor. I will show you the figure. You can see in the figure, at the beginning, whenever there is a we have a say tin oxide, we have taken an example tin oxide, and we have a heater below, and in between we have a alumina substrate. Now the tin oxide, or maybe it may be some zinc oxide also, those materials having a property that whenever there is a air or presence of oxygen, those oxygen will come in touch of those tin oxide material, and they will absorb the electron from there. So due to this, once those free electrons, they are at the surface. So due to that, there will be no flow. If we have a 2 terminals in the tin oxide, 2 sides, you can see 2 terminals are there. So those two terminals, if we apply a voltage here, and we have applied a voltage, but there is electrons are less because they are attracted to the surface due to the oxygen present in the air in the near to the surface. So those electrons are attracted to that surface, and due to that there is the absence of electron, or less electrons are present, so your current flow will be less. But whenever there is a presence of reducing gas in the environment, then in presence of that, those oxygen will not be present, or their amount will decrease, and due to that, those electrons which was actually concentrated on the surface, they will be discharged from that region, and now number of electrons will increase, and there will be current flow in the tin oxide, the layer. So due to that, their conductivity is changing. Means in the presence of the air, normal air, oxygens are enough, oxygens are there is a current flow is less. Now whenever we have a reduced gas, those gases will react with those oxygen, and as there is a number of oxygens are less, now electrons will increase in the tin oxide. Due to that, conduction will increase. So that can be seen as this phenomena can be seen as a detection of those reducing gases. Means, so what it is doing, the trapping of the electrons at absorbed molecule, and the band bending induced by these charged molecules are responsible for a change in the conduction in MOS layer. So here the conduction is changed due to those electron trapping. Now the molecular oxygen absorbs on green boundary region of the MOS layer, and this oxygen traps the free electron in the conduction band. So it is a simple, if it is a trapped, whenever oxygen is present, then it is trapped, it is trapping the free electrons. So obviously in the MOS layer there will be less free electron, and their conduction will be less. But whenever reducing gases are coming in picture, means we are giving some reducing gases in the environment, then those they will react with the oxygen, and this oxygen will relieve those free electrons, and they will be again present in the conduction band of the MOS, those tin oxide, or maybe the other zinc oxide, or those materials. So this is the way how this MOS sensor works. The MOS sensor here. So what advantage we have in the MOS sensor? So advantage actually we have that it can be MEMS MOS sensor has a critical status in gas sensor field like air quality, good health, domestic gas safety. So for those applications, we can easily use the MOS sensor. And the fabrication can be wafer level using the semiconductor process. So earlier, whatever devices we was using or sensor devices we are using, they are big in size. So all the places or all the applications we cannot use it. Maybe for if we think about for the sensing of material, sensing of a gas in a sophisticated a satellite, or anything is leak is there or not. So for those cases, there actually the weight and size matters. For those applications, we always require a very small size and with very good quality, with proper sensitivity, a sensor. So in those applications, actually normally these MOS sensors, MEMS MOS sensors are normally used. Now, so how it can be easily integrated in the ASIC modules, because we are here, we can fabricate these MOS sensors on top of our normal silicon wafer also. So in that way, it can be commercially available, and it can be integrated with the other devices. So beside that, the low, it can be, if it is massively produced, we can have go for the low cost, low power, good response to different kind of gas indicators. So, and other than that, we can use easily, if it is a low cost and small in size, and even low power device, then we can easily use this type of devices for our IoT applications. So there are multiple number of applications where we can use this type of MOS sensor. Instead of the earlier type gas sensor, this type of sensors can be used for multiple number of applications. And even the structure optimization or developing the sensing material with low operating temperatures are effective way to reduce the power consumptions. Now here another important thing is power. So any system, whenever we are designing, if you take an example of satellite or take example any other example, the power is a very important factor. How much power it is consuming. Other type of MOS sensors, we have to use some battery. So if we can decrease the power requirement, then it is advantageous, and obviously we can have a number of applications for those type of sensors. Now, other than that, here how this power requirement is coming. Actually, why this power is so much power is required. Here you see we have told that we have a heater, a sensing material we have, and below that we have a heater. So those heater has to heat those sensing material, and that why it has to heat the sensing material? Actually, the sensing material will sense the oxygen or any other gases at a proper at a specific temperature, because that means to activate that sensor material, we have to give a proper temperature. So to maintain the temperature, we require those type of heater. And now the sensing device or sensing material size and or mass will decide how much temperature, how much power is required. If it is a say for a 300 degree centigrade, if you want to you have to use it, then how much big that sensing material is, how much mass we have on that material, so on that system, so that will decide how much power will be required. If the size or structure is minimized, if we can optimize in such a way that we require a small sensing element, then obviously our heating requirement or heating power requirement also will decrease. That obviously that will reduce the power requirement or power consumption. So here we have explained, we just Though I want to show you that how we can differentiate between this catalytic type gas sensor or electrochemical type gas sensor or MOS type gas sensor based on their requirement of the parts per million. So you can see here for the catalytic type gas sensor or the electromechanical type gas sensor, we require very much more amount of gas. But for the MOS sensor, the wide range we have means we, along with the technology, whenever we are decreasing the size of the MOS sensor, so it is sensitivity and the requirement of the gas also decreases. Now I will give some example. Okay, before example, actually, what parameters we have to look for in this type of our MOS sensor? We have to look for the sensitivity first. With how much sensitivity we have. It is actually change of measured signal per light concentration unit. So, and next is the very important is the selectivity. So selectivity, actually this type of material, those MOS sensor, why we talk about the selectivity? Actually, those MOS sensor is they can sense number of gases. So the change in the material characteristics can be done for different type of gases. But whenever we choose any specific gas sensing, then we have to think about the whether it is responding to that specific material or not. So that's why this selectivity means the sensor for a specific group of analytes, or even as for specify, we will specify the single analyte only. Now the stability of a sensor, which will provide reproducible results for a certain period of time, whether it can reproduce the same result or not for the similar amount of gas. Now the detection limit, how much lowest concentration of the analyte is required to detect through the sensor, that will give us the detection limit. Then dynamic range and the linearity, resolution, response time. So these all are important, but response time, you see here, this is the how much fastly it can to sense the material, how much fastly it can give the changes in the characteristic, and the recover time. If we withdraw the sensing material or analyte, then whether it will recover to its original position or not. So that is the recover time. So, and the working temperature is usually the temperature that corresponds to the maximum sensitivity. So at what sensitivity, temperature it is giving you the maximum sensitivity, that is also important. So some of the presently published, already published the begin. So you can see the material, zinc oxide or tin oxide with other material also in combination, they are they're detecting the carbon monoxide concentration. You can see 1000 ppm. See, it is too concentration is too high. It means maximum it required that one minimum it can it required that 1000 ppm. Temperature is 658 to 680. So and the last one you can see its temperature is 130. So in the most cases, the temperature you see, it is more than the room temperature. It is very high temperature is required for sensing of this the material. So in the second table also, if you see the temperature, these are very high temperature. So that is another issue. If we are going to use a sensor for MOS sensor for combustible gases, if its temperature is more than room temperature, in that case it is possible there is a combustion and it may cause a very disaster in different industry applications, because there we want to detect detect the gas. We don't want to inflame all those gases. So those cases, the temperature is a very important factor. The temperature should be as low as possible, even if it is a room temperature or maybe lower than that. So here, so different volatile compounds also can be sensed for, and these gas sensors are essential for detecting harmful gases in the industry work or war field or maybe the disastrous situation. So there you can see these materials with combination with the other material or maybe they can detect different different type of gases, and but their concentration requirement is different, their temperature is different. So very few are there which are working in the room temperature. So presently people are working to meet this requirement, to prepare the devices, sensor devices, which will meet this requirement of room temperature and with the low power consumption. So there are some more. So this working of this type of sensor, it may be resistive or maybe FET. Some we can use as a FET also for using these materials for different nanowares also can be used for detecting this type of gases. So those we are using for sensing of the gases in MOS sensors. Now I will explain one MOS sensor structure which was proposed by Dongcheng Zi, and here you can see at the top figure we have a very small sensing material which is in the color brown color. This is the sensing material here, and this material actually the size or the mass of this material is very less, and below that we have a detecting electrode which is separated by a gap, a small gap, and we have an isolation layer, and below that we have a heater, and that is supported by a substrate layer. Now in the structure you can see if there is this type of structure, whenever there will be, it's similar to a cantilever structure, we call it cantilever structure. Now in the cavity, if gases are present in the sensing material, whenever it will be heated, in presence of those gases, its characteristic will change, and due to that it will be detected. Now using this type of structure, here it is applied for detection of ethanol, and it has been seen that it is up to 10 ppm level of ethanol with a power consumption of 2.96 milliwatt. Okay, it has been detecting, while for 1 ppm level gas it can be power level may be required more, that is 5 milliwatt. So heating up the time is required is 260 microseconds. So that will actually tell you how much time is required to sense the this gas. Now this type of cantilever structure, and it can be fabricated using the MEMS technology, micro machining we can use, or normal silicon technology, or some of the similar normal silicon technology also, fabrication technology also can be used. The size of the sensor and the amount of sensing material actually limits the heating up time. If the material is mass is more, then our size is more, then the heating up time will be more. Obviously the time taken by the sensor to detect it also will be more. And even along with that, the temperature requirement also, that power, not the temperature will remain fixed, but the power requirement, because we have more mass, then we have to give more power to heat that. So that power requirement also will increase. So this is the a very a good structure where a small amount of power is required to heat up a sensing material, where the heater actually, where this heater is used very small heater, and as the time is less, that can be one thing can be done. We can use the pulse heating. Pulse heating means the heater, that power will be that signal will be given, or the voltage whatever we be applying, that will be given in form of pulse. So if we use it as a pulse in a pulse mode, then the requirement of power also will be reduced. So in this type of structure can improve the MOS sensor, and it can be used for many applications. Now another structure, you can see here the sensing materials are used at the top of a very thin layer of the sensing material used, and in between those electrodes are also been interdigitated. So if we see the side view, you can easily see in the second figure or third figure, if you see the side view, those electrodes are in between, and that one portion is the electrode, then again the sensing film, then again the electrode, then again the sensing film are coming. Now, in such type of structure, what is happening with the presence of the oxygen, the conductivity of the material will change. If there is oxygen is present, then conductivity will change, and means the resistance will change. As the resistance is changed, so at the whenever before we are giving for testing the sensor for a specific gas, before it the resistance will be something, and after the testing, at the time of the testing, the resistance will increase. Means with the oxygen, whatever the reaction between the sensing film and the oxygen gas may result in the significant resistance increase, which was detected to determine the presence and concentration of the test gas. So in this type of structure, actually the ZnO2 and SnO2 combination was used for the sensing films. So it's not that only one material is used. So we can use the combination of some one or two or three materials also. So actually which gas we want to detect, based on that we have to decide whether it should be a combination or whether it should be a single material. So because all the MOS materials, those metal oxides, they have different property. Their structure, crystalline structure are different. So if crystalline structures are, their structures are different, at the surface, the dope concentration of the impurities, that also will be different. So the change in the properties also will be different. If we want to select a specific gas, so we have to select for a specific range, we have to select a specific material, or maybe a combination of 2 to 3 materials. So this is how they work. So there is a possibility that we can design new structures, and based on the structures, its sensing time also can be changed. Its material, if we change the material, its selectivity will change. If we do the fabrication type, how the fabrication is done, in which process, whether it is used PECVD or whether it is normal CVD or any other deposition process, based on that also its properties will change. And design or mass of the those metal oxide semiconductor will decide how much heating power is required, and obviously the heater structure also will decide how much power is required and how much fastly these devices will work. So another device structure, what is that? Titanium dioxide, which is using titanium dioxide based capacitive sensor for detection of hydrogen. So earlier cases, we have seen some other material, now the titanium dioxide. So here actually in the top of the titanium dioxide, we have palladium gate. Now this palladium gate actually acts as a catalyst for hydrogen atoms, and they will hydrogen atom diffusion, and they will get absorbed at metal oxide interface. And due to this, a dipole layer is formed, and this dipole layer subsequently changes the work function of the palladium metal. So based on this characteristic, actually the conductivity also will change. And conductivity, even though as there is a diffusion is happening and there is a dipole layers are formed, there will have change in the capacitance also. Now, using this change in the capacitance and the dipole, capacitance and the conductance, the sensing can be done. So in this type of structure, actually the sensing of 4% sensitivity is seen of 4% for the H2 gas. And in presence of the normal ambient air, it is 84%, and with the nitrogen gas, it is 90%. I will show you some characteristics. You can see with a specific volt, whenever we are applying, we are trying to see the characteristic, means we want to see the conductivity and the capacitance also. Both with the hydrogen concentration, it is decreasing. So, but the change in the capacitance and the change in the conductance are different. So change in the conductance is higher actually with the compared to the capacitance. So if we try to calculate the sensing, or if you try to calculate the sensitivity from the conductance, then the sensitivity will be higher. So you can see the sensitivity is higher in the this figure for the H2 concentration percentage. If it is 1%, obviously the H2 concentration is only 1%, the sensitivity will be less. With the concentration of gas, sensitivity always increases. Even with the temperature also, for a specific range, the sensitivity increases. Now for a specific, we have to give a specific voltage to sense. We can see the sensitivity, how it is changing with the applied voltage. So applied voltage means actually it will decide how much temperature you are giving, and in this case, in this case there is no temperature. Here we are using the current flow. So here with the specific voltage, we can see that sensitivity is more or less near about, the slight changes are there. The characteristics are similar. But if we calculate from capacitance point of view, or if we calculate from conductance point of view, there is a huge difference. So we have to think about which parameter or which characteristics is changing more for a specific MOS structure or a MOS material. So we can sense from the change in the conductance, we can sense from the change in the capacitance, we can in the change in the other parameters also, doping concentration also. So there are many ways how we can see, or maybe the change in the optical characteristics also. So in different cases, it will be different. So we have to, for a specific material, we have to think about which parameter we should choose, and how all the parameters are changing with the change in the concentration, with the change in the voltage, or change in the heating environment, or change in other characteristics. Now we have a MOS to film based ammonia sensor. So there are different publications are done, and fabrications also been done. It is to prepare a flexible ammonia sensor. The flexible means it can be easily tested in any of the maybe in body of the human, or maybe in body of any robot, or in any place. If it is a flexible, it can be easily placed. Maybe whenever soldiers are going in the field, so those whether there is a chemical or different hazardous chemicals are present or they are not, those can be sensed by this type of sensor. So easily this type of sensor can be integrated in the uniform of our soldiers. So for those type of applications, this type of flexible substrate sensors are very much important, and they may be useful for those applications. So here a thin film of MOS was used for a spin coated, actually it is spin coated on polymethyl methacrylate. So, and here ammonium electrodes are used, and these are deposited on a very thin substrate. So here also, as the material is we can think about this is almost only two-dimensional device, or maybe we can say these are one-dimensional MOS devices. Actually, these will be very small. very thin layer. So one dimension thickness is almost near to, we can neglect the thickness, so that's why one dimension is less. And then if the dimension, another dimension is only in some few micrometer, then obviously we can say this is a one-dimensional MOS sensor. So these can be counted as one-dimensional MOS sensors also. So there are multiple other sensors are fabricated using the molybdenum disulfide. Now those will actually, it can sense the hydrogen, it can sense the acetone, it can sense ethanol, it can sense other material also, other gases also. So same material, you can see with the combination of other material can be used for sensing of different gases. Only thing we have to concentrate on the what is the temperature, what is the requirement of the temperature, whether it is a room temperature or not, and how much is the sensitivity, and what is the response time, what is the recovery time, and how much parts per million, or how much parts per million is required for sensing of those gases. So that is very much important. And this, whenever we design, if we want to design any MOS structure, then firstly we have to think about, we have to target which material, which gas we want to select, and we have to choose the MOS material in such a way that for a specific temperature and a specific structure that will select that gas, and means with presence of that gas, it will change its characteristic. So after that, we have to think about other parameters like sensitivity, response time, recovery time. So mostly presently, along with the structure, the temperature requirement and temperature requirement is very important. And so this is, we have to concentrate on this temperature requirement, because if it is a hazardous gas and if it is inflammable gas, then if we want to use a sensor in the industry purpose, maybe some gas pipe, we want to see whether near to the gas pipe there is a leak or not. If we use very high temperature in the sensing to heat the sensing material, then there is a possibility there will be a combustion, and there will be a new disaster may happen due to those sensor itself. So we have to use the sensor in such a way that they should not inflame those gases, and even they will react, they will give the signal for the sensing those gases. So we have to design a smaller and smaller structure, and we have to design the heater in such a way that with the less heating time, with the less heating power, we can achieve our target, and we can sense the specific analyte. So there are actually, we have to, whenever we have to go for the choosing of the material, then we have to think about what are the characteristics of those materials, the surface characteristic, how much diffusion is done on those devices, what is the doping characteristic for those surfaces, then whether it is a transition metal or a non-transition metal. So those things we have to think about, and we have to concentrate on that. Now, these are the challenges which I was talking about. These are the challenges. What challenges we have, and researchers are concentrating on. There is the main challenge is the high selectivity, then the temperature dependency, which already I have talked about. Then means at the low temperature we have to sense with a good selectivity, and even with a good sensitivity also. So proper designing of and proper choice of the material, that is very important. And fabrication wise, we can use the MEMS sensing techniques, MEMS fabrication techniques for this fabrication of this type of sensor. So presently our fabrication is more well advanced, so we can go for a smaller and smaller devices which can be incorporated in the in any integrated circuit, or in a flexible substrate which can be mounted on in the body of, or in the uniform, or any other places, or mounted on in any other devices. So these are the challenges of the MOS. I think I have given some points where we can work, you can concentrate on in future for development of new MOS sensors with a good selectivity, sensitivity, and very low temperature. So here I will, this is the future of the sensor. Means if we can have better sensor in the medical application, diagnosis will be more easier, then performance will improve the performance for energy sources like fuel cell and others, solar power and other things. And for the environment monitoring cases, this type of MOS sensors are very important. And means for the safety and health of, for the health, safety and health, whether there is an emission from any factory or not, that also is can be detected easily if we have a good sensing device. And if it is easily available, if we can fabricate a very small device, then it will be, the cost will be low, then it can be easily available, and it can be used for the home applications also. So I'll stop here. There are some references. Thank you.
Thank you, sir, for your nice presentation. So I think the participant has got benefit on your lecture, with your lecture, and they can start working, because what I have seen that sir has given some avenues in which you can work. So it is a nice presentation indeed, and thank you, sir, for your time. But now we will take up some questions. If the participant is having some questions, please write in the chat box. We will take up the question. So any questions are there? If the participants are there, so participants, you keep the question in the chat box. We will take up the question. Any question from participant side? If you have any question, you can write it to the chat box. So if nobody is writing, I shall consider there is no question, I think. So let's see, just give me 1 minute. Neither in question answer session,
no questions from,
nor in the chat there is no question. So I think there are no question. Thank you once again, sir, for your nice presentation. Dr. Partho Sharathi, he has raised his hand. So can you write the question, Dr. Partho Sharathi? Can you write your question? Can you write your question in the chat box? Dr. Partho Sharathi, can you write your question in the Dr. Partho Sharathi has no question. Okay, so mistakenly, I think the hand has been raised. Anyway, thank you so much, sir. Participants have no question. Thank you for your valuable time.
Thank you, sir.
With this, I am concluding this session. So have a nice day today.
Thank you all the participants.
Yeah, thank you to the attendees for your kind patience, and thank you. We'll be meeting again tomorrow. Okay. Thank you.
Sir, one thing, actually many are having questions regarding the attendance all. So already.
Yeah, regarding the attendance, I think Maiti sir will take care of.
Yeah, there is no problem. If you are attending, automatically it is taken by the Zoom. application. It is already noted whenever you log in, automatically your login is registered, and how much time you are spending here, though all are registered. So I think that there will be no problem if you are continuously attending.
Okay. So
Okay.
thank you.
I think, okay. Thank you, sir.
Thank you.